Hello and welcome to week 6 of Instrumentation and Measurement in ME397 at the University of Evansville. So far along the course we've been considering static measurements, things that really don't involve time as a variable. And this week we're going to change it up a little bit by bringing time into the picture, discussing dynamic or time-varying measurements. And along with that will come subtopics including sample aliasing, and we'll learn about first-order measurement systems, how they respond to common inputs like a step function or a sinusoidal input. Believe it or not, this topic is relevant to many of the things you're trying to do within your design projects. For instance, the Mini Baja vehicle team have been wanting to do drop tests to measure accelerations with different suspension settings. Well, in that case, when you drop the car, it's going to oscillate in response because the suspension system has springs and dampers associated with it. So the question is, how often do I need to sample data from the accelerations to be able to catch the peaks and the troughs, the movement of the suspension through the acceleration? And this issue is directly tied to sample aliasing. So consider the known, where we understand that analog signals are continuous in time and amplitude. You can look on the screen here at this image. The solid black line would represent some sort of a constant, or a continuous rather, analog voltage signal. The issue is digital signals are not. Digital signals are discrete. We take one measurement at one instant in time. So how many discrete signals must we take to accurately represent an analog signal? What must that delta t be in between measurements to be able to accurately reproduce the signal? And the signal is described by frequency. How often does it repeat itself? So this depends on the frequency content of the measured analog system, and it could be a signal that's a combination of several different frequencies. That's directly tied to the increment size between each discrete system, and also the total sample period. Those are the things that drive our decision on how often to sample data. At this point, we should talk about terminology with data acquisition systems. Usually you don't speak in terms of the delta t or the wait time between measurements. Instead, what you'll more often hear is the sample rate, which is just the inverse of that. How many samples per second are taken? And if your units are per second, the units are hertz, inverse second. So instead of saying, for instance, wait 1/100th of a second in between samples, we would say have a sample rate of 100 hertz. Now, the important theorem here is called the Nyquist sampling theorem. And it tells us that a signal will appear as an alias or a false frequency when the sampling rate is less than 2 times the maximum frequency you want to measure. So your sampling frequency, S sub s, must be greater than 2 times the measured frequency. And since the sample frequency is 1 over the wait time between samples must be less than 1 over 2 times the measurement frequency. Thus, we can say that we're going to have false or alias frequencies if my sample rate is less than 2 times the measured frequency. And we call that the limit the Nyquist frequency. So the Nyquist frequency f sub n is equal to the sample frequency divided by 2. Let me show you an example. Okay, in this example, let's look at the top left graph, and that represents a signal that I wish to measure. So some sort of instrument is producing a dynamic signal varying with time that oscillates between 1 and -1 volts. And we see that in 1 second time it completes 10 oscillations, 10 periods. So its frequency is 10 hertz. 10 cycles per second. Okay. Well, the Nyquist sampling theorem would say that in order to accurately capture the frequency content of the signal, I would need to record at twice that rate, so at least 20 samples per second. What would happen if I did not do that? Okay, so for sake of example, let's say I incorrectly set my data acquisition system to record at 12 Hertz. Okay, well, the Nyquist frequency in this case is going to be half of that. So 12 Hertz divided by 2 equals 6 Hertz. Okay, so any signal above 6 Hertz, I'm going to expect alias frequencies. So what would I expect? Well, this is called a folding or fold-down chart, and I can use that to determine what the alias frequency will be. I'll take my incoming frequency and divide that by the Nyquist frequency set by my sampling rate, and that's going to be about 1.67. Well, I can come up here and find 1.67. There it is right there. And I can just fold that down to the base axis. And I see that my alias frequency is about a little bit above 0.3. We'll say my alias frequency in this case is about 0.3 times my Nyquist frequency. Well, since my Nyquist frequency was 6 Hertz, 0.3 of that is going to give me a 2 Hertz alias signal. And that is this case here. Note that we have the 12 Hertz sampling rate, and you can sort of match this to the picture above. If this is the original signal, I'm taking a sample every 1/12 of a second. So it turns out, I take my first sample here. My next sample is taken somewhere here. I'm matching these dots up on this screen. My next sample is taken somewhere here, it would appear. And then my next sample is taken somewhere here, etc. And you end up, when you reconstruct your signal based on the data you've taken, you end up with something at a much lower frequency. In this case, 1, 2 oscillations per second, or 2 Hertz. So hopefully you can see in this example how important it is to set your sampling frequency much higher than your input signal. Look at the other cases. What would happen if I met the Nyquist sampling theorem and sampled at 27 Hertz? 20 is my minimum, and I sample at 27. Well, when I connect the dots, I don't exactly get the original signal. However, I am pretty much able to find the peaks, and I am able to determine the frequency. If I want to resolve the peaks better, then I'm going to have to choose several multiples of the Nyquist frequency. So for example, in this case B, I could sample at 100 Hertz, and in that case you see now I'm getting multiple samples at all over the incoming frequency, and I'm able to pretty much resolve the peaks and troughs of my signal. Let's talk a little bit more about how measurement systems respond to dynamic signal inputs. The naive view is to think that we can just throw some sensors on our system and take measurements, and those will perfectly match the real signals we're trying to record. A measurement system is always going to output information regardless of how well or how poorly that might reflect the input signal. So to figure out how the output of the measurement system relates to the input from the signal, we have to calibrate it, calibrate the dynamic system. Very similar to how we would calibrate a static system by putting in a input and observing the output, and for doing that for different circumstances. Now, however, time is a variable, so we have to look at dynamic signals and how those affect the dynamic output of the measurement system. To do this, we start by proposing a general mathematical model for the measurement system, and then we perform a calibration, a dynamic calibration of the system, and we do that to figure out the parameters of the mathematical model. Let's start with our mathematical model for the measurement system. We'll start here visually with just a black box that is our measurement system, whatever that would entail. And it has an initial condition before any signal is sent to it. And then we send it a signal. And that input signal is some sort of function that varies with time. And as a result, the measurement system produces an output signal. And that signal also varies with time. So the question then is, how does this output signal depend upon the initial state, the initial condition, and the input signal? So this summation describes our measurement system under different scenarios. And let's look at three of the most common cases. Okay, and the three cases all vary depending upon how the instrument responds with time to a signal. Well, if we do a one-term summation here, I equals 0 to 0, then we have the zeroth derivative, which is just going to be the signal itself. And this then becomes this equation. So we have one constant, so A is a constant. We have Y, which is our signal output, and we have F, which is our system input. We call that a zero-order system. If I do a two-term summation, I equals 0 to 1, then I have my zero summation, and then I have a first-order derivative and another constant. So I have a constant first-order derivative plus a constant zeroth derivative equals my input signal function. And then a second-order system will do three terms. So we bring, in other words, the second derivative of the output signal in. And you can see we have essentially three different kinds of differential equations as a result. Let's look at a zero-order system first. Here's our zero-order system model. So here's the mathematical model, and then we'll algebraically rewrite it to where it represents some physical things. So we'll divide through by the constant, and we end up with y equals 1 over the constant times the input signal. And we'll call that k. And now this looks just like our static system sensitivity, right? We have y, which is our output from the measurement system, and we say it looks like the input times the sensitivity. Notice that the time doesn't appear anywhere else in the equation, so we have an instant output response to a system input. And then if we want to find that k factor, the static sensitivity of the system, we would perform a static calibration. We'd find the slope of the calibration curve. In other words, if I have my input and then I have my output, y, I would take lots of different data points and fit a trend line to that. Excuse me, there we go. And then the slope of that trend line would be my static sensitivity. Now let's look at the more interesting case of a first-order measurement system. For the first-order measurement system, note that we have a derivative with respect to time present. So now this system has some sort of response due to the effect of time in the input signal. Well, we'll say that a first-order system is a measurement system as a result that has some sort of a physical storage element which keeps it from responding immediately to a change in input signal. In other words, there's a lag. In general, any system with a storage or some sort of dissipative capability, but negligible inertial force can be modeled by a first-order differential equation. Again, we have the mathematical model, and we can re-express that such that the parameters now have physical significance. So what we'll do is divide through by this constant A0, and we'll call this ratio tau, Greek tau symbol, or a time constant. Remember, we have the 1 over A, which we saw before is physically is the static sensitivity. What does this mean? Okay, well, the time constant is the measurement of how fast the system responds to an input. And thus, the smaller value of tau for the time constant, the faster the system is going to respond. Well, now that we've seen that a first-order system has some sort of delayed response to an input signal, we need to figure out how big that delay is, how it responds to different types of signal inputs. Well, there are two very common simplifications of a model input. You can either say a model or a signal input is a sinusoidal type input, or you can say it's a step function type of input. Most signals can be simplified to one of those two. What do I mean by a step function input? Well, that looks something like this. So I have time on my x-axis, and I have step function on the y-axis, and that can vary from 0 to 1. In time, we'll have -1, 0, 1, and 2. So what happens is, for time below 0, I have 0 input, and then as soon as I hit 0, that instantaneously steps or switches to a value of 1. Now, in reality, nothing can respond instantaneously, but this is good enough for very rapid events. For instance, if we were measuring something in a pressure tube or a diaphragm burst releasing a high-pressure gas, that would be a step function type of input. Or if you took a thermocouple and plunged it into a cold or hot water bath, that could be modeled as a step function type of input. Well, what does that do? Well, it changes my signal input to this step function, and I can multiply it by some sort of amplitude if I want this to be greater than 1. And for times less than 0, I have 0 input, and then for times greater than 0, I have step input. And that now replaces my function input to my first-order differential equation. And we need to solve this. To solve it, let me first rewrite it a slightly different way to maybe help you see this more clearly. So my derivative is dy dt, and I'll move the time constant around. I'll divide through. And hopefully you see that this is a first-order linear differential equation. From Math 324, you've learned that you can solve this type of equation using an integrating factor. Integrating factor. I believe the textbooks usually call that Greek mu, and it's equal to e raised to the integral of this constant in front of the dependent variable. So for us, that's 1 over tau integrated with time. And that integral is easy to carry out. We end up with t over tau. Well, to use this, we multiply it by both sides of the equation. We can do that with the rules of algebra. And if we do so, we end up with e raised to the t over tau times dy over dt plus e raised to the t over tau y over tau equals e raised to the t over tau times ka over tau, that should be a, there we go, times my step function. Well, the thing that the integrating factor did was turn the left-hand side into something that can be collapsed via the chain rule. Hopefully you can see or convince yourself that this is the same thing as the derivative of e raised to the t over tau times y. If I take the derivative of this using the chain rule, I end up with this exactly. And that then is equal to the right-hand side, which I'll write okay. Well, we are one step closer because now we can integrate this equation. We can separate the variables and integrate. Let me multiply by dt over here. So on this side, I end up with the derivative of e to the t over tau times y. And then on the right-hand side, I'm going to end up with k a u over tau e to the t over tau dt. And I can integrate both of these sides. Let's do that. I'm going to integrate this from 0 to t, and then I'm going to integrate this expression as well from 0 to t. Okay, I'll move up here. Now, if I integrate this from 0 to t, I'm removing the derivative, and I evaluate this then at those two locations. So here's my intermediate step. I end up with e raised to the t over tau times y of t, and evaluate from 0 to t. And then my right-hand side, I'm integrating this with respect to time. And we see time is sitting right here. I can carry that out, and I end up with Ka over tau times tau times e raised to the t over tau, evaluated from 0 to t. Well, so I can carry out the evaluations now, and on the left-hand side I'll have e raised to the t over tau times y evaluated at t minus, when t is 0, well, e to the 0 is 1, so I'm just left with y evaluated at time 0, whatever that is. And then on the right-hand side, let's see here. When time is 0, e to the 0 is 1, so I'll just have Ka. And then when time is t, I will have Ka times e to the t over tau. And there's my time 0 result. Okay, we're getting somewhere. This is what I want, right? This is the output of the measurement system with respect to time. So I can isolate that. And I'll end up with, I'll rewrite it this way, Ka plus, and then I'll group together y0 minus Ka multiplied by e to the minus t over tau. Another way of looking at this, I can say y of t, my system output, looks like, now Ka was my input signal. My input signal is my amplitude multiplied by my static sensitivity. So this is the system response after a lot of time has passed. So I'll call that y0, or my steady state response. Plus y0 is my initial condition. I can shortcut that by just calling it y0. Here again is my system response after a lot of time has passed, multiplied by e to the minus t over tau. Okay, so here is my solution to the whole shebang. This is how a first-order measurement system is going to respond in time to a step function input. There are two ways to view this response. One is in terms of percent completion. And here's what I mean by that. I'll come over here and I'll take the equation we ended with on the previous slide. Y infinity plus y naught minus y infinity times e to the minus t over tau. And let's see here, I'm going to algebraically regroup it. So I'm going to multiply everything out right now. So that's going to give me e to the minus t over tau times y naught. And then I'll have minus e to the minus t over tau times y infinity. Now let's further try to switch things around here. I can subtract both sides by my initial condition. Bear with me. And I'll just put it right here. That's my initial condition, plus e to the minus t over tau times y naught. And by doing that, I can factor some things out. I can factor e to the minus t over tau out of this grouping and this grouping. And that looks like, algebraically, one minus e to the minus t over tau times y infinity minus y naught. And then finally, I can write it this way, yt minus y naught over, and I can divide this over, y infinity minus y naught, and that equals 1 minus e raised to the minus time over tau, my time constant. Okay, what does all this mess do for us? Well, it shows us a, this will be unitless, right? I have response over response, so whatever those units are, they will cancel out. And this now is an easy function I can graph. So let's do that. Let's draw this in a nice big graph. So my x-axis is going to be normalized time. Time divided by the time constant. Okay, my y-axis is going to be this grouping. So I've got y minus y naught divided by y infinity minus y naught. This is the total change in the signal between initial and final, and this is the current difference between what the system is outputting and what the initial condition was. Okay, so we see this type of exponential response. What happens when time is 0? Okay, so our system is receiving a signal, and when time is 0, I have e to the 0 is 1, 1 minus 1 is 0. So when time is 0, my measurement system is not outputting anything, even though it is getting a system input. Okay, it's not able to respond because there's a lag. And then what happens as time passes, this exponential gets smaller and smaller, and the system passes more and more information. I'll break this into a few factors, 1, 2, 3, 4, and 5. So after one time constant has passed, I end up with 1 minus e to the minus 1. This is going to look something like this. 1 minus e to the 1 gives me 0.632. Okay, so after one time constant of time has passed, the system has responded with 63.2% completion. It's still not passing all of the input signal. Note the full step occurs about 4 or 5 time constants after. By the time you've gone to 5 time constants, you end up with just about 100% completion. I'll make that a little bit higher there. Okay, so I've put in a step. Let me, I can draw that here, right? Here's my original sort of signal. Okay, so black is the original signal. And then the red is my measurement system. So you can hopefully clearly see now the delay caused by the measurement system. We're not able to immediately measure the output after 1 time constant has passed. We still have only measured 63% completion, and it takes about 5 time constants before you're effectively measuring the original input signal. A second way to view the step function response is via an error fraction. So for that, let's look at our solution again, and we'll group it a little bit differently this time. So remember, my system output equals y infinity plus y naught minus y infinity times e raised to the minus time over time constant. Okay, I'm going to call my error fraction capital Greek gamma. And what I'm going to do is bring this over and then divide through by this quantity. So I'll have my system response minus the system response after a lot of time has passed, my steady state response, and then divide it by this grouping. And then I'm left with, on the right hand side, e to the minus t over tau. Well, I can graph this similarly to the way I graphed the last example for completion. This time, for error fraction, on my x-axis I'll have normalized time, again, this quantity, the time elapsed divided by my time constant, and 0, 1, 2, 3, 4, 5. And then on the y-axis, I'll have my error fraction. And you'll see this error fraction goes from 1 to 0. So when time is 0, e to the 0 is 1. So I'm up here. And then as time increases, e to the negative increasing number makes this quantity get smaller and smaller. So we see that this decreases exponentially. And it turns out that after 1 time constant of time has passed, I have e to the minus 1, which gives me 0.368. So you can view this as percent completion or percent error left in the signal. So after I've sent a step impulse into my measurement system, after 1 time constant has passed, I have 63.2% completion of the response. I still have 36.8% error. It takes 4 or 5 time constants for the system to have responded completely to the input. Now, the error fraction you can actually view graphically. For instance, I could take the natural log of both sides, so the natural log of my error fraction, and then I could take the natural log of this side, and I would end up with, I'll write it this way. And then I could graph this. And then the graph should show a linear relationship, right? This would be y-axis. This would be my slope, and this would be my x-axis. So you could actually test a measurement system to a step function input and then graph it to calibrate. And by calibrating, I mean you can figure out what the time constant is of the measurement system. Once you know the time constant, then you realize it's going to take 4 or 5 time constants in time before the system is able to accurately measure an input signal. Here's an example that you're actually going to perform during our lab practice this upcoming week. It turns out a thermocouple can be used as an example of a step function input. A thermocouple, we'll talk more about temperature measurement a little bit later in the course, but it consists of 2 dissimilar wires joined via soldering. And due to their different conductivities of the 2 different wires, the wires generate a voltage, electromagnetic force, that varies with the temperature. So it's a transducer that turns a temperature change into a voltage change. Schematically, here's the solder bead. And we know that solder bead has a thermal mass, so it takes time for it to come into equilibrium with its environment. We'll use the first law of thermodynamics to help us model this. See how this is a first-order measurement system. Well, remember, we can write the first law of thermodynamics for a control system. So I'll draw my control system around the thermocouple solder bead here. And that would tell me that the change in energy inside the system with time is equal to the rate of heat transfer minus the rate of work between the system and the surroundings. Well, let's look at the left-hand side. This is the same thing as saying the change in internal energy with time plus the change in kinetic energy with time plus the change in potential energy, there we are, potential energy with time equals rate of heat transfer minus rate of work. Well, hopefully you can see that no work is going to be done in this situation, and we're not going to really see any change of kinetic energy or any change in potential energy. So what we have is a balance between internal energy and heat transfer. Well, this is an incompressible substance, so we can model our internal energy change using the specific heat of the solder material. So mass times specific heat times how the derivative of temperature, which is a function of time. That must then balance with the rate of heat transfer from the fluid to the system or from the system to the surroundings. Okay, and then what is my heat transfer? Well, my heat transfer is going to be convection. We have this fluid, whether it be a liquid or gas, and it has a convection coefficient, so we can use Newton's law of cooling to model the heat transfer via convection. And that looks like the convection coefficient times the surface area multiplied by the temperature difference between the surrounding fluid temperature and the temperature of the thermocouple bead. So let's combine all of this and come up with a mathematical model for plunging a thermocouple into a fluid environment. So doing my combination, it's going to look something like MC. Since those two are constant, they fall outside of the time derivative. Equals H times surface area times T infinity minus T. And this looks like a first-order differential equation. I can regroup it to make it look like my general first-order measurement system. So I'll group all of the parameters or constants together. Okay, this is looking like something. What if I take all of these guys together and say that's equal to 1 over time constant? If I do that, then I have something that looks very similar to my first-order differential equation for a first-order measurement system. Okay, so I need to solve this. How do I do that? I'm going to move like terms over, separate variables. So I'm going to move temperature to the left-hand side and everything else to the right-hand side. That's going to give me the temperature over temperature minus T infinity. And then on the right-hand side, I'm going to have 1 over that grouping of constants that I'm calling 1 over tau times the derivative of temperature. And well, I can integrate this with respect to temperature. I can integrate this with respect to time. And going through that then leads me to the natural log of T minus T infinity. And that's evaluated from my initial temperature to my final temperature. And on the right-hand side, that's just going to give me 1 over tau times T evaluated from 0 to times T. And I'll finish that out. The natural logarithm, algebraically, subtraction turns into a fraction. So I can write this as that fraction equals time over the time constant. Wait a minute, that looks just like my definition of the error fraction that I showed a couple slides ago. And we see then that the time constant, so where the time constant is defined as mass times specific heat over the convection coefficient times A. And the units, right? This should be units of time. And so if we look at this from a dimension point of view, well, mass would be in kilograms. Specific heat would be in something like kilojoules per kilogram degree Kelvin. My convection coefficient is in watts per meter squared Kelvin. And my surface area would be in square meters. So carrying this out, remember a watt is a joule per second. So everything cancels out except second, and we're left with seconds for my units. So that checks out. And in doing this, we've assumed that the material properties do not change with temperature, they're constants. We've assumed that the wires that are attached don't transfer any thermal energy. And we've assumed a lump system, so there's no conduction inside the bead. There's just convection heat transfer that's dominating how things change with time. But you'll actually be using this, so you can take a thermocouple and measuring some sort of temperature in the room, and then you can plunge it into an ice water bath very quickly. Well, that approximates a step function input in temperature, and the system will respond accordingly. As we saw previously, you can take this information. We can raise both sides. We can plot this as my y-axis data on a chart, and we can plot this as my x-axis, and we can determine what the time constant is of the thermocouple as a result. So not every input signal can be modeled as a step function event. In that case, another type of very common input signal could be something that's periodic or varying in time, like a sine function or a cosine function. In that case, our mathematical input would look like some sort of periodic signal, a sine signal, with a frequency omega and an amplitude a. And initially, nothing's coming into my measurement system. And then at time 0, this input is applied. So my first order model for my measurement system, I take my input signal and I replace it with a sinusoid. And I won't go into the mathematical solution process, but you learn this in Math 324. It ends up looking like some sort of a transient part that dies away with time, and then some sort of steady state response that oscillates at the same frequency of the input signal, but with a different magnitude and maybe a different offset. And these constants, the B term, the C term, and the phi term here, all depend upon the frequency of the input, the time constant of the system, the amplitude of the input, the sensitivity of our system, and the initial condition. What does this look like? Okay, well, after the transient has died out, so I let at least 5 time constants pass, I'm left with an oscillating output from my measurement system. And this graph here shows the solid line, which is my system input, my signal input to the system. Okay, it has an amplitude and a frequency. The dotted line, on the other hand, represents what the measurement system is outputting. And you see that it is of reduced magnitude, the same frequency, same number of oscillations per second, but it has a reduced amplitude and it has an offset as well. And those are the two things, primarily the amplitude change, that we need to understand. So to see how this magnitude change is a function of frequency and time constant, what we'll do is define this magnitude ratio. So magnitude ratio is capital M, and we'll call it the amplitude of the output signal divided by the amplitude of the input signal. Okay, remember B is the amplitude of my output equation, and my input amplitude is A times the static sensitivity of my measurement system. Well, I carry that out and I'm left with 1 divided by the square root of 1 plus omega squared tau squared. So my system output depends both on frequency and time constant. We see that when this product is very small, I have 1 over 1, which is 1. So on this graph I have that the measurement system is outputting the same magnitude as the input signal. But then as this product becomes larger, I start to divide through by a larger number, and the magnitude ratio, or the output, decreases. And as this gets higher and higher, the output decreases even further. This is not what we want. An example is a RC circuit as a signal filter. You've actually done this in your circuits class. Help you remember here that there are 4 basic filter designs. We can have a low-pass filter. So there's frequency. So here's a low-pass. And the low-pass filter for my magnitude ratio, right, and there's 1. So it passes all frequencies up to some sort of a cutoff. So there's frequency cutoff. So we have our pass band, and then we have our stop band. Another type of filter is a high-pass filter. Here's my magnitude ratio. In this case, I am not passing lower frequencies, but then I come to my cutoff frequency, and now I do pass all of my frequencies. This is high pass. I could combine these and also form a bandpass filter, something that selectively only passes some sort of a band of frequencies. And then the fourth and final type of RC filter is a notch filter. So for that, we pass all but a small section of frequencies. An example for this would have been cable TV providers. Not currently, everything's digital. But back in the analog days, if you wanted to have some people that paid for basic cable and others that paid for the full package, you could maybe use something like a bandpass or a notch filter. A combination of resistors and capacitors on the line that either added static to the signal or cut static out of the signal to allow you to see the higher channels. Note that these are ideal filter characteristics. In real life, you don't get the ideal response, immediate change at a certain frequency. Instead, you have a drop-off. And you saw in your circuits class that transition is called the filter roll-off, and it's given in units of decibels per decade. Here's a graph of a low-pass filter. So the most common type is a Butterworth filter, which has a flat magnitude ratio over the pass band and then a steep initial roll-off slope. The cutoff frequency, or the break frequency, is defined at that point at which the power is reduced by 1/2 by the first order system. And the power being reduced by 1/2 is the same as -3 decibels, which is the same as a magnitude ratio of 0.707, square root of 2/2, I believe. And the frequency bandwidth is then all the frequencies that pass with a deduction of greater than 70%, or I guess I should say less than 70% reduction in the signal. So we have our passband region here, and then we have our cutoff region here with our roll-off slope, again in units of decibels per decade. And finally, we'll see exactly how the RC circuit acts as a first-order system. For instance, the low-pass filter. Well, here's my RC circuit. So I have my signal that's coming through a resistor in series and a capacitor in parallel. And then I'm measuring my output here in parallel with the capacitor. Well, the current goes through the loop as shown. So the current must be the same through the resistor and the capacitor. Well, the current through the resistor must be equal to the voltage divided by the resistor, or the resistance. And the current through the capacitor must equal the capacitance times the derivative of the voltage. I can rearrange this and show that, hey, this is a first-order differential equation. There's the derivative of output voltage with respect to time. And the time constant is a function of RC, the resistance and the capacitance. I could create a high-pass filter by putting the capacitance in series and the resistor in parallel. And in that case, I could rewrite my equation. And if I use my dependent variable as the change in voltage, I could once again end up with a first-order differential equation where the choice of resistor and capacitor dictate my time constant.